Dampness in Buildings and Diagnosis, Module 6. Sources of damp, rising damp. Cases of severe rising damp, and I think these really are severe and exceptional, and there are 3. However, probably more commonly encountered rising damp, and basically this is the stuff I encounter. 2 examples there, you can see these and the damp patches. This is where the damp proof course is not proved effective, basically. This is flooding and not rising damp. The diagram on the left shows the result of flooding. You get these concentric rings. The water rises up in the plasterwork or whatever, and then it dries down, leaving these concentric rings. This particular property had a retrofit physical damp proof course, and there was a flood in the end of the property, and that was fixed and it dried down in stages, leaving the concentric marks. We can define rising damp as the passage of groundwater up through masonry. The water rises through a series of interconnecting pores by a process loosely called capillarity. In other words, the porous masonry simply acts like a wick. A more simplistic view is that if the suction of the wall is greater than the suction of the ground, then water will rise. If not, then water will not rise. Thus, water does not automatically rise where there is no damp proof course. This of course depends on pore structure and other factors. Capillarity and hydrostatic pressure. Capillary movement, water movement in small pores caused by the surface tension of the liquid with the side of the pore. There is no pressure forcing this movement. Rising damp is simply due to capillarity, the material acting like a wick. On the other hand, hydrostatic pressure is the pressure of water exerted under its own weight or gravity. Hydrostatic pressure will force water out of capillaries and the water will collect. Hydrostatic pressure has nothing to do with simple capillarity and does not force water up a wall to form rising damp. How high can water rise? Well, the height is governed by several factors. 1, the pore diameter. The narrower the pore, the greater the height of rise. 2, obviously, pore continuity. The pores must be continuous up the wall. And 3, evaporation. And that is affected significantly by the presence of hygroscopic or deliquescent salts. Indeed, all things being equal, which of course in reality they're not, water will rise to a greater height in a thick wall than a thin wall. This is to do with the surface to volume ratio. In a thick wall, the surface to volume ratio is smaller than it is with a thin wall. Thus, on a thin wall, evaporation plays a greater part. Height of rise continuing. Pore size in bricks and mortar can be as small as 1/1000 of a millimetre in radius. Average 0.1 millimetre. Pore size of that size, 1.01, gives us a theoretical height of rise of around 1.5 metres. Thus, rising damp can rise well in excess of 1 metre, a height frequently claimed to be the maximum. Indeed, the highest level I've come across by profiling gravimetric methods was 2.5 metres. The other thing that's important with rising damp are the moisture pathways up a wall. And if one thinks about it, the mortar beds are usually the only continuous pathway up a wall through which water can rise. In order to move from brick to brick, it must cross a mortar bed, and therefore it would not be continuous. So the continuous pathways are the most important part, namely the mortar beds. So we know from earlier on we get salts distributed in rising damp. Those are groundwater salts. All kinds of materials are present: soluble chlorides, nitrates, sulfates and other mineral salts and soluble materials. And with the rising water over a very long time, usually, we get a build-up of these salts. And the typical distribution, we get a salt concentration at the top of rise, known as the salt band, and no significant levels, typically at the base of a wall. And very important, if you are looking for salt contamination, the result will depend on your sampling position. Common effect of long-term rising damp. Seen this often in walls around villages. We have a salt band. We can see that, this obviously damp band. And if we look at a wall in general that's had rising damp or got rising damp, the lower part will contain groundwater salts as long as free moisture. The upper part will be clean. And indeed, it's the presence and distribution of groundwater salts that are almost unique to rising damp. And it is the key to its diagnosis, the distribution of moisture and salts. And we saw this earlier in an earlier module. Features of rising damp versus condensation, well, there they are. You can do the comparison for yourself. Eruption of finishes doesn't usually occur with normal condensation, although I have seen simply in showers a bit of paint peeling, but I think that is fairly straightforward. And of course, there is very broadly a condensation season, and that is between September and April. But as I say, that is a broad definition. So how do we diagnose rising damp? Well, we looked at some of this earlier on. Use of an electrical moisture meter, high meter readings at the base, slowly declining upwards and the sudden cut-off. There's quite a nice note in the Property Care Association's DP1 use of moisture meter, which states it's not satisfactory to check the performance of a new damp-proof course in a building that has suffered from rising damp. In such cases, salts will be present to a greater or lesser extent, whether the new DPC is effective or not. These salts alone can produce high readings. Well, fundamentally, they shouldn't do if you've got a decent dry lining or replastering system. However, if we are going to use a radio frequency meter or capacitance meter, then remember, these will pick up materials deeper in the wall. So back on to the diagnosis of rising damp. Again, this was covered earlier. The basic moisture profiles, non-effective DPC or no DPC. Remember, the salts mark the history of the rising damp, namely the maximum height to which it once rose. In this case, the salts and the free water are rising to the same height. Secondly, controlled rising damp. Damp once rose as indicated by the distribution of salts to a much higher position. Free moisture is now only rising to a small proportion of that position. Finally, the third one is we can see that we had rising damp as indicated by the presence and distribution of salts. However, there is water going much higher than the level of salts. This simply indicates a further source of water ingress, in which case you cannot tell how any damp-proof course, if installed, is performing, because one doesn't know how much water at the lower levels of the wall is due to continued rising damp or water penetration. We now come to have a look at retrofit damp-proof courses, chemical retrofit damp-proof courses. They consist of a two-part process. The first is the injection process, and that, and I emphasize this, controls the damp. The second part of the process is the replastering or dry lining, and that is designed to prevent future spoiling. Chemical damp-proof courses are a system, and in essence, the two parts are inseparable. If you require a dry non-spoiling surface, they are inseparable. They should be regarded as a control system in that they control moisture but are unlikely to stop it like that of a physical damp-proof course. Hence the replastering or dry lining to give us a dry non-spoiling finish. So here's a complete appearance of the two. Physical damp-proof course, complete impervious barrier across the wall. Chemical, a diffuse band of a water repellent or pore blocking agent. There is a British standard relating to chemical damp-proof courses, and that is 6576 Code of Practice for Diagnosis of Rising Damp in Walls in Buildings and Installation of Chemical Damp-proof courses. It describes 4 systems. High pressure, these are based on solvent systems. You don't think you really come across them much nowadays. Most of the stuff now is either low pressure, usually water-based systems. There's gravity transfusion used for aqueous-based systems as well, very rare at the moment. And finally, hand insertion used for injection mortars and thixotropic creams, the latter being by far, I think, in nowadays the most common. So looking at the materials themselves, solvent-based systems, they're applied under high pressure. Silicon resin or polyoxoaluminium stearate, POAS, 4 to 5% in white spirit or other aliphatic petroleum solvents. Those materials are initially water repellent. Water-based systems, they're applied by low pressure or gravity, potassium or sodium methyl silicate in water. Both those materials are initially water soluble. So how do they work? Well, the process takes around 2 weeks to complete. We start off with the siliconate, a water soluble material, which reacts with carbon dioxide and goes through a process, and we come across the material at the bottom, which is a water repellent silicone resin. Going on with damp-proof coursing, hand insertion, the silane siloxane thixotropic creams, and more recently the silane siloxane impregnated rods. It's the plastic rod, very permeable, full of the appropriate silane siloxane. Simply drill a hole and it's pushed into the hole in the mortar. How does water repellency work? This goes for silicon resins, POAS, methyl siliconates once cured, silane siloxane creams. Basically, water repellents line the pores of a material. They do not block the pores. Usually in the case of the silicon and aluminium based materials, the silicon is bonded with the aluminium is bonded to the surface of the pore, and the methyl groups, the stearate groups, stick out within the pore, and these form the water repellent surfaces. Water repellent action. Water repellents are pore liners. They change the surface tension of liquid with the side of the pore. The contact angle changes and water rise is stopped. On a treated material, the contact angle becomes greater than 90 degrees and water does not rise. On a non-treated pore, the contact angle is less than 90 degrees and water will rise. Continuing with basic damp-proofing materials, hand insertion is the second one. Injection mortar is a pore blocker, and the way this works is that holes are drilled, rather large holes are drilled in the mortar beds down at an angle of about 30 odd degrees, and the injection mortar is put into the drilled holes and the materials diffuse between the holes in the mortar. The material is a siliconate. How does it work? Well, injection mortar basically consists of ordinary Portland cement, sodium carbonate, silica, tartaric acid, the latter being there to slow the set. When mixed, they form sodium carbonate plus silica. These two together form sodium silicate, which is soluble, that diffuses through and into the mortar beds where it reacts with calcium and form calcium silicate, which is insoluble, and this blocks up the pores in the mortar. Outline of the installation processes, BS6576, high pressure, low pressure, gravity feed, hand insertion, thixotropic creams. These are the basic outlines of the installation, hole diameter, depth, and, where appropriate, the pressure and how to apply. All damp-proof courses should be installed not less than 150 mm above external ground levels, and care must be taken to account for any changes in level. And internally, they should be installed as close as possible to a solid floor. Where the floor is a timber suspended type, it needs to be inserted beneath the timbers. If that is not possible, then one must take precautions to protect the timber, because it is now below the DPC. However, full details on the installation processes and conditions are found in the British Standard Code of Practice for Diagnosis of Rising Damp in Walls of Buildings and Installation of Chemical Damp-Proof courses. So how does moisture now move then in bricks and mortar? Well, let's imagine this. First scenario, impervious mortar and permeable brick. If the mortar is impermeable and the bricks are permeable, then water cannot rise. It cannot move out from any bricks at the base of the wall. So we do not get rising damp in such a situation. Alternatively, if we've got impervious brick and permeable mortar, then water can still move and rise because the mortar beds form the only continuous pathways up the wall. They can bypass the bricks. And ideally, all damp-proof courses should be installed in the mortar beds. It is the mortar beds that are the most important. We also have another advantage of drilling mortar beds, and we can drill the holes in the mortar beds, and these break the path, or at least some of the path, of the dampness to prevent it rising. One of the problems with high pressure injection, which now is really more of historic pressure because I don't know anybody who actually uses it, is that when the injection is applied under high pressure, the DPC forms fingers. It does not push out the resident moisture in front of it. It simply forms fingers which follow the lines of least resistance. These, of course, leave holes of resident moisture through which water can still rise. Bridging, number there, these are taken from Building Research Digest 245, Rising Damp in Walls, Diagnosis and Treatment. Some forms of bridging are more important than others. Some are relatively minor and really aren't going to cause much of a problem. Sometimes just simply boil down to a floor-wall junction problem. We often come across problems associated with a cavity wall, dampness at the base, and it's very careful not to put or run straight into the fact it's rising damp. So what are the sort of items one should look at in looking at a cavity wall? Plaster taken below floor level, plaster taken behind damp-proof membranes, plaster bridging DPC, solid floor bridging DPC, floor DPM cut short, DPC or DPM continuity between the two, debris bridging the cavity, water transmission via cavity insulation, high ground levels, damp-proof course not complete through the leaf. Those are possibilities, are the major possibilities. The least likely option is a non-functioning physical damp-proof course. So then we ask the question, how effective are retrofit chemical damp-proof courses? Well, basically, if we look at them and look at them properly, they will do anything between nothing and something. They do not cause negative effects. They'll do something or nothing, anything between that. If there is a specific problem with a chemical damp-proof course, it did not fail. Basically, it did not work in the first place. They're not put in and then subsequently fail. They're put in and just don't work. Chemical damp-proof courses are unlikely to stop rising damp like that of a physical. Furthermore, they are less effective in genuinely wet walls. My experience is the wetter the wall, the less likely they are to be effective. However, they should control the rising water to a greater or lesser extent, so that in association with specialist replastering and deep dry lining systems, a dry non-spoiling surface is obtained. So for all intent and purposes, once we've got to this stage, we have visually a dry wall. Other damp proofing systems, they're non-chemical, they're not British Board of Agrimon certified. There's the electro-osmotic system, which are around and are reported to be effective. The other systems basically are atmospheric governed systems, the Shriver system and porous tubes. They work on atmospherics, they require air exchange. Of course, that is enormously variable depending on wind direction and wind strength and whether anything is on the outside of the wall that can prevent decent air access to that wall. The question that's always asked, do you really need to insert a chemical damp-proof course? If the dampness is only rising to just above skirting, no, they will have no real effect. If it's like that, then the answer is simply to investigate the floor-wall junction. If the wall is distinctly wet, don't rely on the performance of the damp-proof course. Whatever the case, they are effectively a control system, and water is still very likely to pass above the height of the injection. Flooding does not affect the performance of a previously installed damp-proof course either. Is the problem sufficiently obvious to warrant an installation? But considering this, remember, timber in contact with dampness will be at risk to rot. And finally, it is rare for a physical damp-proof course to break down. Dampness in buildings and diagnosis, end of module 6.